Great. So yeah, thank you, David and Ron. It's an honor to actually be able to give this talk. I never got to work with Carl, but I mean, yeah, he's certainly been a big influence. Um, and thank everyone for showing up for this. As David said, this is super early for me, but perhaps not for everybody else. Okay. So yeah, I'm going to talk about some theory work we've done dealing with biologically motivated learning dynamics in sort of two different ways. So I'm going to tell two different sort of short stories, if you will. One about extensions of or thinking about the constraints imposed by an architecture, not necessarily the learning rule, but what is learned when you impose something a biological constraint on the architecture, and the other an extension on the dynamics of Hebbian learning. And so I guess I will start the first story with what in this day and age has to be a fairly staggering understatement, that hierarchical computation is an advantageous thing. These structures are important, apparently, both biologically and computationally. We're probably familiar with the ventral stream, which does a successive processing in the macaque. And of course, starting go all the way back to Fukushima, you have convolutional neural networks, which, at the time, perhaps were not widely recognized, but by this day and age, of course, they've sort of led to a revolution in machine learning that now everybody sort of carries in their pocket some implementation of things like this. Uh, but back to biology, not only do you have these streams, you typically often have multiple computational pathways. One that's often talked about is the ventral and dorsal streams carrying, for example, object properties versus spatial awareness properties, or local versus global motion pathways, or any number of other parallel type computational pathways that generate different kinds of features and different kinds of computational properties. Now, at the Allen Institute, of course, one of the things that we do is produce these large-scale data sets to ask various questions, and one of the premier data sets is the mouse connectivity atlas. The analysis of which shows that the visual system in the mouse doesn't look architecturally very much like the macaque, in the sense that there's an obvious single serial computational pathway, but rather you have sort of the initial sort of V1 layer, which is what we call VisP. VisP is the Allen Institute name for V1. But instead of having an obvious a serial pathway, it's actually quite broad. And so if you wanted to try and convert this to some sort of an analog of the macaque ventral stream, you might actually create parallel pathways, which is in fact what we did. So we created this convolutional. We tried to map this structure to a convolutional net that we creatively called MouseNet, that was intended to be sort of a parallel, if you will, of the sort of standard ventral stream model. But because of the architecture, we built it with these very parallel streams. And I probably should have included a picture of the mouse anatomy just for those of you not familiar with it. But anatomically, what you have is V1 or VisP in the middle, and a lot of these other areas sort of surround it in the periphery. In terms of the pathways, it looks like these are all sort of parallel. And when we tried to train this thing, we trained it, and since they all led to this upper visual area, we trained it on sort of one cost function. We wound up getting a situation where basically sort of one channel would take over, and you get sort of garbage in the other channels as a frequent example. So we wanted to know if we could understand what was going on and explain this. And so that led to us creating a very, very simple computational model or analytic model where we wanted to see if we can understand what would happen in a simple feed-forward network with parallel pathways. And I've drawn a network with two pathways, but in principle, you might imagine, 3, 4, 5, whatever arbitrary number, and of arbitrary depths in each pathway. And so in this case, I've got pathway A and a pathway B. Here, they're the same depth, but they might in principle be two different depths, depending. And importantly for this, we're thinking about the context where you have one input and one output and one cost function that all the pathways hit. You might imagine, since I talked about, for example, local versus global motion or ventral versus dorsal, it's a perfectly reasonable thing to imagine you have multiple pathways and then a cost function for each pathway. So you might have some convergent, some common features, and then a divergence because pathway A needs to do task A and pathway B needs to do task B. We're asking a little different question. What happens if you have parallel paths that all contribute to the same cost function? And so what we're going to do is approach this in sort of a regression framework. And so we're going to minimize the mean squared error here, where x is the input, y is the output, and capital omega is the global, I should say global, the total computation of the set of channels in the network. In this case, just a sum over the different channels. In this case, we have m channels. Now, this is just regression. It's a regression, against whatever the set of features that this network produces. And as such, the total solution, provided you make an assumption about the coordinates of the input, is just that the network will learn to imitate the input-output correlations of the training set that you give it. Now, this I've said this perhaps in a way that might be unfamiliar depending on your background, but this is really just the results that you see in your machine learning technique textbook for linear regression. Normally, the weight functions go to the input-output correlation divided by the input correlation. So this is a kind of network that, or rather, Sachs and Andrew Sachs and colleagues analyzed a deep linear network with one single channel. And one of the things they did was to demonstrate that the learning dynamics sort of reduced to thinking about, or could be reduced to thinking about what happened to each singular vector of the input-output correlations. And so if you have, for example, a classification task where you're trying to put object properties on different kinds of objects, this is going to deconvolve into different singular vectors that describe the different important relationships between the objects, whatever objects you have and the properties they possess. So a question that arises here in this framework is sort of what happens to the singular vectors for each of these object properties when you have multiple channels. And so I'm going to ask kind of an obvious straw man kind of question, a leading the witness sort of question, because you might think a priori that, pathway A is going to learn a little bit of one singular vector, and pathway B is going to learn the rest of that singular vector, and so on. So you get sort of this perhaps random or somewhat random distribution of singular vectors across the different channels. Or you might imagine, for example, that pathway 1 says, no, I'm going to take singular vector 1. Pathway 2 says, I'm going to take singular vector 2, etc., and they segregate. And of course, I'm asking that for a reason, because that turns out that's, of course, what happens. So we're going to analyze this in following the same linearized framework that Andrew Sachs and colleagues did. So we're going to throw away the nonlinearities for mathematical tractability, and then we'll post hoc ask whether that was a reasonable thing to do. We're going to look at this in the regression framework. And if you then take a gradient descent approach and take the continuous time limit of gradient descent over large input batches, you wind up with this equation here at the bottom for the gradient descent. And so I want to point out a couple things. One being this equation, or this expression in brackets here, which is basically the expression you would get from linear regression, where you want to match the input-output correlations with the output of the network times the input correlation. But you also have all these effects from the multiple weights. And so one of the things I want to emphasize is that you have one effect that's sort of this regression matching effect that's going to have an explaining away effect later, as it does in linear regression. And then you have this power iteration effect from having trying to force your features through multiple layers. And both of those two effects are going to be important in what we're talking about. Okay, so the framework we're going to use, we're going to make an assumption of infinitely wide networks. And we're going to make an assumption that the initial weight values are drawn from a zero mean Gaussian distribution with a variance of sigma squared over n. One of the things this does is let us take the initial conditions and play a little bit of a game where because of that limit, those two things we're considering, those are the initial conditions for each weight matrix for the mapping each layer to the next layer are effectively orthogonal matrices, and so we can use them as a coordinate system. And so what we're going to do is change to a coordinate system in the singular vector space, and so that changes that weight dynamics to an equation that looks very similar. I've put bars over the w's now to denote that they're the weight vectors in that space. But now this regression cost function term in the middle is just s minus omega bar, where s is just the diagonal matrix of singular values. Furthermore, we're going to make a diagonal ansatz for each of those weight matrices, which is not a huge, that might sound like a strong assumption. In fact, most of them start out diagonal anyway because of the initial conditions. And so it's actually a relatively weak assumption, but we wind up decoupling all of the singular vectors when we do this. And in fact, you can do a little bit of massaging. and you wind up with actually a relatively simple equation for the dynamics of a coordinate for each of the singular vectors for each channel. So just to unpack this a little bit, we have this coordinate P for each channel A and each singular vector alpha. We have this set of dynamics for the alpha singular vector S. And of course, in steady state, it's going to match the singular vector expression for the output of the entire network. And importantly, this omega bar here is the sum total of all of the channels, and so it combines the effects of all of the channels, and this is where the channels sort of interact with each other. Okay, so if I look at the dynamics of two channels against each other, and so this is the coordinate for one channel versus another channel, I can plot some phase planes here. And so what I've done here is on the top row is one specific set of initial conditions. So I do the same 100 conditions, and all I'm changing is the depth as I go from left to right. And so you see what happens is the phase flow starts to diverge more and more for the same initial conditions as you increase the depth. The only difference between the top row and the bottom row is the standard deviation of the initial conditions. So you have a wider spread for the top row than the bottom row. Of course, in the limit, where everything is precisely at the origin, so if there's no noise whatsoever, then everything is going to go just to you have complete symmetry, and everything is going to go right to the middle of this marginal attractor here. But in general, things are going to be away from that origin, and that deviation from the origin is going to wind up driving things apart. So there's sort of two things going on here. One is you have an explaining away effect from the linear regression, because each channel is like a feature that's trying to explain, if you will, the output features, but at the same time you have a power iteration from going through the depth of the network, and that amplifies small differences. And so those two things sort of compete to have an effective kind of, not a precise winner take all, but sort of an effective approximate winner take all solution, so that in the limit, these finite size effects turn into a sort of exclusionary winner take all effect for one of the channels. And so basically what happens is that singular vector concentrates on one particular channel, and that happens independently for each singular vector. So we can do this, we can simulate this for a small network. And so here over on the left, I've got the evolution, or for each of these four plots, I've got this plot of the evolution of each of the dynamics for each of the singular vectors for each channel. And then I've got the final state in the singular vector space for each channel. And this is the global effect of the channel, not any particular layer. And so you see for d equals 2, the singular vectors wind up just basically splitting roughly evenly. All of the curves are sort of sitting on top of each other. Both channels are sort of doing the same job in this case. You have a very weak explaining away effect, if you will. As you increase the depth, you start seeing that winner take all effect, so that by the time you get to depth equals 7, each singular vector has picked a particular channel to live in. So now, importantly, this was done in a linearized framework. So real deep networks are rarely linearized, because you could collapse the whole thing. But in fact, if you do the same, do these exact same simulations with hyperbolic tangent or ReLU, you get the same results. Qualitatively, they do the same thing. The hyperbolic tangent, you could argue that the analysis, in some sense, still topologically applies, even though the exact equations become more difficult because of the smoothness. ReLU, you have to do a little more work, but empirically, the result seems to hold. Now, importantly, you might say, well, this is kind of a small example here. In fact, this is a situation where the entire data matrix is in the paper, as opposed to, we reference some giant data set like ImageNet or something. But in fact, I claim that the experiment we wanted to do had already been done, or at least one version of that. And so if you, at least in machine learning terms, if you go back to the dawn of time, or the Stone Age, or if you will, and look at AlexNet, one of the first major convolutional neural networks, they actually, because of the time period and the computational constraints they had, they actually implemented this on 2 GPUs in a roughly parallel pathway. There's a little bit of interaction between the pathways, but by and large, this is a parallel pathway stream. And one of the things they observed is that in fact, one GPU learned by and large one set of features and the other GPU learned a different set of features. So GPU 1 by and large learned textures and GPU 2 learned colors. And so I would posit that we have a potential explanation for why this observation happened, and a potential mechanism for why you might get feature differentiation in pathways that all feed similar cost functions. So if you have a architectural pathways in the brain, for example, and all of them subserve some similar function, this kind of mechanism might contribute to feature differentiation. Okay, so that was sort of story one. This was a work with a graduate student, Ira Shih at the University of Washington, who's co-advised with Eric Shea Brown. And just to sort of reiterate, we looked at sort of multi-pathway deep networks in a linearized framework, and we showed that you wind up with a tendency for singular vectors as a function of as depth increases to concentrate on a particular single pathway. Okay. So now I'm going to pivot. And so that's an architectural constraint where we say we want to study learning, but we're going to specify the architecture looks like the following in a particular network. Now we're going to go look at how changing dynamics might affect the learning. And in this case, we're going to look at sort of something that's probably familiar to almost everybody on who's shown up for the talk, which is Hebbian learning. But just to get everybody on the same page, right? Hebbian learning is this notion where if two neurons are sort of coactive, they will in some sense reinforce each other. The sort of fire together, wire together idea. Now, there's a classical expression of this, which is in lots of textbooks that people are probably familiar with. But again, just to establish some language, so you have some neuron that has a vector set of inputs, and there's a set of weights that multiply each of these inputs, and that goes through some nonlinearity to determine some output. And you're going to update the weights according to some learning rule along with some normalization. And the traditional classical Hebbian learning rule here is that you take the product of the input and the output. And so when you take the continuous time limit of this particular set of dynamics, you wind up with the following equation, which is often referred to as the Euler rule, which has this nice expression where the evolution of J goes as some matrix product with some matrix with J itself, where that matrix is the input correlations. And then you have this normalization term, or this extra term that serves to help normalize the J's. Otherwise, you'd have a runaway solution. Now, importantly, J transpose mu J here is a scalar, and so the steady state winds up being the eigenvalue equation for this input correlations. And so the steady states are the eigenvectors of the correlation of the input statistics. And so you can see let me run this again. Evolution, an example of this where this J vector moves to the largest principal components of this particular set of input statistics that we're using to train. And that's an important thing here, is that what's on the slide at the moment just says the steady states are the eigenvectors. It turns out the only stable eigenvector in this case is the largest eigenvector. And that's in fact what you get is the largest eigenvector is the unique solution. Okay, we're going to generalize this though. So we're now going to ask the question, what happens if we take a learning rule where we have sort of a multi-point, sort of what you might think of as a multi-spike learning rule. You can think of the Hebbian learning rule as what happens if you have a single presynaptic spike and a single postsynaptic spike, and you take sort of a mean field rate limit of that, and you get that product rule. So now you imagine a rule where you have multiple spikes, multiple spikes in the input and output, and those are required to generate some sort of weight update, as well as perhaps some dependence on the weight itself. So in this case, we stuck to a particular a polynomial form for simplicity. And this generates a generalization of the dynamics that looks like the following. So this is formally very similar and bears a lot of similarities to the Euler rule, whereas now we have these more complicated structures. So first of all, just to interpret some things, there's this sort of tensor product here where you have the A-fold outer product of J is what this is. Alpha here is a multi-index. So you have, depending on what A and B are, you'll have multiple indices, in this case, A indices. And mu I comma alpha now is a more complicated moment than just the correlations of the inputs. It's actually this high order multiple moment, depending again on B, um, and the number of values being dependent on A here. And so now you have this sort of tensor product, or at least a term that involves a tensor that comes from the statistics of the input. And then similarly, you still have this normalization term that prevents J from blowing up, that derives from this normalization of the weight update. Okay. Again, similarly, with the you wind up with a scalar term here. And so in the steady states, you have this sort of generalization of the eigenvector equation that determines the steady states for the Hebb rule. In this case, this is now what's called a tensor eigenvector, or I guess depending on what you choose for A and B, this is now a different kind of a tensor eigenvector. So there are two that are known. For example, if you pick C equals 0, that's one kind of tensor eigenvector. If you pick C equals, excuse me, A plus C equals 1, so that the exponent over here is A, that's a different kind of tensor eigenvector. And they'd have different mathematical properties. They have different enumerations. They're different orthogonal transformation properties. And so depending on what you choose for your plasticity rule, you'll get different tensor eigenvector problems. Okay, so here's an example of simulating that. So now instead of taking dots from a multivariate Gaussian distribution, we're actually feeding natural image patches, which don't have Gaussian statistics, into one of these networks, and we're watching it learn. And so on the top here, on the right, you have just the weights of that vector, and on the bottom, you have the angle between the eigenvector to which it's converging and the vector that's doing the learning. And you see there's this sort of transition right as the vector collapses onto the vector that it's converging to, where it has learned to simulate that particular vector. And so you've solved this sort of tensor eigenvalue problem. Okay, but even better than that, we can actually do some analytics on this where in certain cases. And so the case I'm going to show you is the case where B equals 1 and C equals 0. And we're going to assume mu is orthogonally decomposable. And we're doing this precisely for analytic convenience, because this lets us actually do some transformations to write down some exact equations. And so we're going to assume there are orthogonal components that you can decompose your tensor into. And you wind up getting different cases based on which powers you pick. So in particular, the parity of A becomes extremely important, whether it's even or odd, and I'll unpack that as we look at some examples here. Okay, so first thing we can do is take the these. Let me go back for a second. These vectors that define the orthogonal decomposition, and we can project the weights onto those vectors. And so we get these similar to the singular vectors in the previous problem, we get these basis function components. Now, if you've unpacked the Euler rule and looked at solutions to that yourself, then this equation is going to look very familiar to you. If I set A equals 1, that's the exact equation you get for each of the components for the Euler rule. And that's the equation you would use, for example, to determine the stability and fixed points and so forth. So in a similar way, so to do some of the similar calculations, if I multiply through by V equals 1, I can get the self-consistent equation for this term L, which is just the last term here. And you can show that the sum of the squares follows this particular equation, which shows you that the steady states are all sitting on the unit sphere, or in this case, the case I've shown on the right, the unit circle. So on the right, we have a case where we're assuming that there are two orthogonal components in my decomposition of mu. And so I have a set of steady states. In fact, there are 8 steady states determined by this particular equation. Only 4 of them are stable, and they're the ones that correspond to the cardinal directions. This is very similar to the Euler rule so far, where all of the different eigenvectors happen to be steady state solutions, but in that case, only one of them is stable. Okay, so we can add, null lines for the different components, but importantly, If you look at you can see what I'm about to say by looking at the ratio of any particular components, and that follows the following equation. Now note, A equals 1 is the case where we get the Hebb rule again. So if you have A equals 1, this ratio dynamics just goes as the difference in the eigenvalues. And so depending on, if one eigenvalue is bigger than the others, that ratio is going to increase. If for the eigenvalues that are not bigger than the others, that ratio is going to decrease. And that's exactly what you get for the Euler rule. When you don't have that case, you wind up getting a different kind of steady state for the ratio, depending on the ratios of the eigenvalues, when A is not 1. And that produces these separatrix lines here, this big blue X here, which separates basins of attraction for each of these different steady states. And so that's if you remember nothing else about this section of the talk, this is the important thing. The largest eigenvector is no longer unique. So that's the important thing about the classical Hebb rule, is you always get the largest eigenvector. For the tensor, for this sort of tensor extension of the Euler rule, you don't get unique solutions. Importantly, though, importantly, so this is the case for A odd, where you wind up with this symmetric phase diagram. The case for A even, you wind up with kind of a problem depending on how you look at it. So note that this bottom quadrant here, where all of the V's are zero, or all of the V's are negative, if you start outside the unit circle, this is unstable. And so that will never converge. That will just explode. And so if you think about practical implementation of this algorithm, that's going to, you'd have to take care to make sure that you controlled that in some way, or you'd have to add something to your equations. You might think for a real situation, R might be very large, and this is a very low probability event, but it's still a possibility nonetheless. Okay. So one of the things we can do here is look at the size of the basins of attraction. And so, for example, if you're implementing this algorithm, or you're imagining an implementation of this algorithm of these dynamics in some particular system, the initial conditions have to come from somewhere. And so in this case, we're just going to imagine there's a hypercube that's surrounding the unit sphere, and that hypercube is going to the initial condition is going to be randomly distributed amongst that hypercube. That allows us to compute the volume, which is going to be proportional then to the probability that eigenvector happens to be the one that's selected, assuming that's how you pick your initial conditions. And so it turns out you get this nice expression dependent on the products of the ratios of the eigenvalues. Now, there's a difference here. This only applies strictly for A odd. For A even, you wind up having to think a little bit more, in particular because of that unstable region. And so what it turns out is you can still compute these things, but this turns out to be a lower bound on that particular on the volume of that basin of attraction. Okay. So back to the simulation I showed earlier. We have this sort of transition in the synaptic weights for when the vector finally converges, and the overlap of the vector with the eigenvector that it's converging to goes to 1. And instead of getting a unique eigenvector over different runs, you wind up with a distribution of the final state eigenvector that's being learned, which goes as, monotonically decreases with the order of the eigenvector. So or I guess against the order of the eigenvectors. The largest eigenvector is the one that winds up getting selected most often, because it has the largest basis of attraction, because it's the largest eigenvector, has the largest eigenvalue, and then the second most, etc. So you wind up with this nice distribution of things that you're converging to. Okay, that went a lot faster than I expected it to. And so this was in this case, the second story is a simple generalization of of Hebbian learning. Importantly, whereas Hebbian learning gives you sort of matrix decomposition of the input correlations, this generalization winds up giving you tensor decomposition effectively. And the important thing is that, unlike the Hebb rule, this solution is not unique. You wind up getting distributions of solutions that go as powers of the ratios of the eigenvalues. Okay. So there are, this is basically two stories from two papers that appeared in Neurops over the last few years. One as I said, was with a graduate student at UW Applied Math. It was co-advised with Eric Shea Brown. And then the second was with Gabe Ocker, who was a scientist in my group at the Allen Institute, who is now a professor at Boston University. So with that, I guess I will conclude, and thank you.